Hello and welcome back. In the previous video, we looked into some common ways of preparing haloalkanes and haloarenes. In this video, we will discuss about some of their physical properties and then we will look into some polyhalogen compounds that are used in our day-to-day lives. Starting with the physical properties, we look into general properties like color, odor. Then we will look into the melting and boiling points, density, and we will end our discussion with solubility. General properties. Alkyl halides are colorless when they are pure. However, bromides and iodides develop color when exposed to light. Many volatile halogen compounds have sweet smell, so that's the order. Next, melting and boiling points. These are important from the examination point of view also and pretty interesting to learn. Compounds such as methyl chlorides, methyl bromides, methyl chloride, etc. are gases at room temperature and the higher members or liquids or solids. When we compare these compounds with the parent hydrocarbons, we notice that the intermolecular force of attraction, which includes the dipole-dipole interaction and the van der Waals interaction, are stronger in case of the halogen derivatives because of the greater polarity as well as higher molecular mass. Because of this reason, chlorides, bromides and iodides have higher melting points than those of the parent hydrocarbons. The attractions get stronger as the molecule gets bigger in size and have more electrons. So for given alkyl groups, the boiling points of alkyl halides decrease in the order of Ri more than Ibr followed by Rcl followed by Rf. That is, Rf has the least boiling points for a given alkyl group. This is because with increase in size and mass of halogen atoms, the magnitude of van der Waals forces increases. The boiling points of isomeric haloalkanes decrease with increase in branching, which we have seen in Unit 12 of Class 11. For example, 2-bromo-2-methylpropane has the lowest melting point among the three isomers that are possible because this has the maximum number of branching possible. Boiling points of isomeric dihalobenzenes are very nearly the same. However, when we come to melting points, para-isomers have high melting point as compared to ortho and meta-isomers. This is because of the symmetry of para-isomers that fits in the crystal lattice better as compared to ortho and meta-isomers. So basically, it's because of the symmetrical nature of crystal lattice. So with that, we have finished melting and boiling points, and now we come into density. Bromo, iodo, and polychloro derivatives of hydrocarbons are heavier than water, and hence the density increases with increase in number of carbon atoms, halogen atoms, and atomic mass of halogen atoms. Next, let's look into the solubility of these compounds. The haloalkanes are very slightly soluble in water. Let's try to find out why. So, for a compound, in this case haloalkane, to dissolve in water, we need to break the interactions between the haloalkane molecule themselves and the hydrogen bonds between the water molecules themselves. And this requires some energy. However, after this breaking takes place, new attractions has to be set up between the haloalkane and the water molecules. However, in this case, the energy released when these new attractions are set up are less because they are not as strong as the original hydrogen bonds in water. So since the energy requirements are not met, the solubility of haloalkanes is less. So now we have looked into the solubility of haloalkanes in water. Now what about organic solvents? Amazingly, haloalkanes tend to dissolve in organic solvents. This is because the new intermolecular attractions between the haloalkanes and the solvent molecules more or less have the same strength as compared to the ones in the previous step, that is, the strength between two haloalkanes themselves and solvent molecules themselves. So before moving on to the next concept, Let's do some exercise. So here are the questions. You can pause the video if you want. I will solve this question in the next 10 seconds. Okay, let's solve. The question says us to arrange a given set of compounds in order of increasing boiling points. So part A, we have given with bromomethane, bromoform, chloromethane and dibromomethane. By the way, bromoform is a common name given for CHBr3. If you have not got it till now, let me give you a hint. Boiling point increases with increasing molecular mass. So in the given set of compounds, chloromethane will have the lowest molecular mass, followed by bromomethane, then dibromomethane, and followed by bromoform. So we've got the answer over here. Chloromethane has the lowest boiling point, bromomethane, followed by dibromomethane, and bromoform has the highest among these. Next, part B. We have one chloropropane, isopropyl chloride, and one chlorobutane. In this, we have to see the branching. That is, the thing with more branching has lower boiling point, and so isopropyl chloride has lower boiling point than 1-chloropropane. And again, we use the fact that boiling point increases with molecular mass to compare 1-chloropropane and 1-chlorobutane. So we have the answer. Isopropyl chloride has the lowest boiling point, followed by 1-chloropropane, and 1-chlorobutane has highest among them because of higher molecular mass than 1-chloropropane. I hope it is clear. If it's not, I advise you to go back to the video and go through the boiling points trend again. Let's move on. Let's go to polyhalogen compounds. In this chapter, we will look into dichloromethane, commonly known as methylene chloride. Then we will read about trichloromethane, commonly known as chloroform. Then triiodomethane, iodoform. Tetrachloromethane, that is known as carbon tetrachloride. Then we will discuss something about freons. And finally, a compound which you would have heard by now, that is DDT, which stands for dichlorodiphenyl trichloroethane. So let's start with methylene chloride, that is dichloromethane. This compound is widely used as a solvent, as a paint remover, as a propellant in aerosols, and as a process solvent in the manufacture of drugs. It is also used as a metal cleaning and finishing solvent. So these were some uses of this compound. Next, we will move on to some side effects or harmful effects of this compound. This compound harms the human central nervous system. Exposure to lower levels of methylene chloride in air can lead to slightly impaired hearing and vision. Higher levels of methylene chloride in air cause dizziness, nausea, tingling, and numbness in fingers and toes. In humans, direct contact with methylene chloride causes intense burning and mild redness of the skin. Direct contact with the eyes can burn the cornea. Even though this compound had so many good uses, it comes with some side effects. So it is necessary to use these compounds wisely. Next, we will move on to chloroform, that is trichloromethane. So what's the use of trichloromethane? Let's see. This compound is employed as a solvent for fats, alkaloids, iodine, and other substances. It is majorly used in the production of Freon refrigerant, that is R22, and it was once used as a general anesthetic in surgery, but now it has been replaced by less toxic, safer anesthetics such as ether. So since it was used as an anesthetic, you might have guessed that it depresses the central nervous system also. So here goes the first effect, that is, inhaling chloroform vapors depresses the central nervous system. Breathing about 900 ppm of chloroform, that is 900 parts of chloroform per million parts of air, for a short time can cause dizziness, fatigue, and headache. Chronic chloroform exposure may cause damage to liver and to the kidneys. In liver, the chloroform is metabolized to pause gene, and some people develop sores when the skin is immersed in chloroform. So let's look at pause gene in detail. So chloroform is slowly oxidized by air in the presence of light to an extremely poisonous gas called carbonyl chloride, which is commonly known as phosgene. You might have come across this compound phosgene in P block chapter. So let's look at the reaction. 2 moles of chloroform when oxidized, that is plus O2, in the presence of light H mu, gives 2 moles of phosgene and 2 moles of HCl. So because of this oxidation nature of phosgene in presence of light, the chloroform is usually stored in closed dark colored bottles completely filled so that the air is kept out. Next, we will look at triiodomethane, that is iodoform. The iodoform was used earlier as an antiseptic, but the antiseptic properties are due to the liberation of free iodine and not due to the iodoform itself. And because of its objectionable smell, it has been replaced by other formulations containing iodine. Now let's look at tetrachloromethane, that is CCl4. It is used in the manufacture of refrigerants and propellants for aerosol cans. It is also used as feedstock in the synthesis of chlorofluorocarbons and other chemicals, pharmaceutical manufacturing, and general solvent use. It was also widely used as a cleaning fluid, both in industry as a degreasing agent and in home as a spot remover and as fire extinguisher until mid 1960s. There is some evidence that exposure to carbon tetrachloride causes liver cancer in humans. The most common effects are dizziness, light headaches, nausea, and vomiting, which can cause permanent damage to nerve cells. In severe cases, these effects can lead rapidly to stupor, coma, unconsciousness, or even death. Exposure to CCl4 can make the heart beat irregularly or even stop. The chemical may irritate the eyes on contact. When CCl4 is released into the air, it rises to the atmosphere and depletes the ozone layer. We all know what happens if ozone layer is depleted. That is, ozone layer depletion is believed to increase human exposure to ultraviolet rays, leading to increased skin cancer, eye diseases and disorders, and possible disruption of immune system. Let's look at freons now. The chlorofluorocarbon compounds of methane and ethane are collectively known as freons. They are extremely stable, unreactive, non-toxic, non-corrosive, and easily liquefiable gases. Freon 12, that is CCl2F2, is one of the most commonly used freon in industrial purposes. It is manufactured from CCl4, which we saw previously, by Schwarz reaction, which we have seen in the preparation of haloalkanes and haloarenes, that is in the previous video. These are usually produced for aerosol propellants, refrigeration, and air conditioning purposes. Most freon, even that used in refrigeration, eventually makes its way into the atmosphere where it diffuses unchanged into the stratosphere. In stratosphere, freon is able to initiate free radical chain reactions that can upset the natural ozone balance. Finally, we will move on to DDT, that is the last compound that we are going to see. DDT was first chlorinated organic insecticide. The use of DDT increased enormously on worldwide basis after World War II, primarily because of its effectiveness against a mosquito that spread malaria and lice that carry typhus. However, problems related to extensive use of DDT began to appear in the late 1940s. Many species of insects developed resistance to DDT. It was also discovered to have a high toxicity towards fish. The chemical stability of DDT and its fat solubility compounded the problem. DDT is not metabolized very rapidly by animals. Instead, it is deposited and stored in the fatty tissues. If ingestion continues at a steady state, DDT builds up within the animal over time. The use of DDT was hence banned in the US in 1973, although it is still in use in some other parts of the world. So before concluding, let me show you the structure of DDT. We have two carbons in the main chain in the bottom left, which is substituted with three chlorine atoms. Hence we have the name trichloroethane in the main chain. Next we have a chlorine substitution in a phenyl ring at para position, and two of these are attached to the second carbon of main chain, and hence we derive the name pp-dichloro-diphenyl trichloroethane, where P stands for para. So with this we have come to the end of this video. In this video we talked about the physical properties of haloalkanes, then we looked at some polyhalogen compounds. In the upcoming videos I would like to talk about the chemical reactions of haloalkanes and haloarenes. I hope everything was clear in this video and hoping to see you in the next videos. Thank you and goodbye.